Hello, folks. Good evening. Hello, folks. Good evening. Welcome to Geek Night, Coimbatore, the 65th. We will be starting shortly. Sorry, there are some issues here, but welcome again. This will be Geek Night, Coimbatore Edition 68. This Geek Night is specifically hosted by the Autonomous Vehicles Tech team here at Coimbatore. We have two topics for the day. The first topic will be embedded pipelines, and the second topic will be Rust in Automotive. To take up the first topic, I'd like to invite Harish, who's a consultant with us and majorly works on getting up embedded system pipelines up here for AV Tech. Hello, Harish.
Cool. Let's start. Hi people, I'm Harish Kumar. I've been working for past 1 year in ThoughtWorks as consultant graduate developer, and I'm working in AV Tech team. So today we're going to see about the topic embedded pipeline in automotive. How a pipeline can be set up for the automotive specific application that we build. So main thing, what is embedded pipeline is building an images which goes into the CI/CD system along with hardware testing and software testing. So that is especially what we call as embedded pipeline. The main three things, the three jobs that we should come across is the software and loop testing. That is whatever the image that we build, the application should run on it. And the application, which is the image which is built for the hardware target, should be flashed automatically. And then the hardware should be tested along with the application in it. So these are the three jobs that we should be taking care when we come to the embedded pipeline. So next is, you see is the next car that you may own will be the powerful computer with you. Why? So this is the AV architecture, in-vehicle architecture, where you could see there is a lot of domains. Like as domains are the main controllers, which will be specified to corresponding domain. So for example, ADAS, Advanced Driver System, is a domain which controls the driving part, and there is another domain called infotainment and powertrain, etc. So each domain is a microprocessor, not a microcontroller. It is it's a powerful one because this application is a mission critical application. So where people's lives is taken care of. So there will be lot of services been running in the backend. So these are microprocessors, and whereas to this will be connected with camera, radar, and those things will be controlled by the microcontrollers for the particular hardware. So for particular hardware, and that is the sensor. So now this is the architecture. Moving on to the next one is, this is the adaptive AutoSAR standard. So what is AutoSAR? AutoSAR is an automotive open system architecture. It's a consortia by a group of people in automotive tech companies, where they come together and they build a standard so that in future the applications can be built on it, so that it can be used by all the people. So if you see here, the hardware will be in the bottom baseline, and there will be running, there will be containers or VMs will be running on it. And above that, there will be an operating system. And above that, there will be the components which is required for a user application that to be built. For example, if you wanted to open, close the door inside in the car, so that is an application. So that will be lying here. So for that, we will be like using all the components, and which will be running on operating system and will be running on the hardware. So this is one standard given by the adaptive AutoSAR platform. So yeah, moving on to the next one is, this is the most complex one which will be available in the software defined vehicle. This is given by the Autoware.io as a reference platform, the one you saw before. So this one is just a single line. So in a real car, you'll be having on a single hardware, you'll be having multiple workloads will be running on. So one workload will be the safety workloads, and another one will be the microservices workload. So this is totally isolated from this, so that all the safety and mission critical services will be running on it. And whereas this one is exposed to other additional services. So if you see here, this is the firmware which is running on the hardware, and there will be the hypervisor which is working on it, and there will be each services running on each OSs. So this is why I told you for the first, the car will be the most powerful system that you'll be owning in the next few years. So okay, now we saw all these things. Now we should know how to build a simple application and to run on it. So for that, here comes the Yocto. Before going to this, I would like to ask you a question. How many of you people have used Linux Ubuntu? Nice. So since it is an open source, not like an Windows, you know how this is being created. Or if you wanted to create your own Linux system, you know how to create this your own system. That where comes to this Yocto and Bitbake. So Yocto project is open source tool which helps in creating your own embedded custom Linux image. So Bitbake is a tool used by Yocto where it schedules tasks so that it can be created, so that the image can be created. So if you see here, this is the overall architecture, how a target image is being built. So finally, for example, I'm taking an example as we are trying to build a target for the NVIDIA Jetson. It's like a Raspberry Pi, a single board computer. So the target image will be the Jetson. So what are the things we require? All should be specified in a built environment. So I will tell you this. The smallest thing that you will be putting into a Yocto image is the recipe. So the application recipe and the image recipe. Image recipe is the final image that we want to build, which will be flashable into the hardware. So this both consisting of a meta layer. So this layer should be specified along with the distribution that we are giving. So now we have used Poki, which is a reference distribution of Linux. And we have our own board specific layer. For example, if you are using NVIDIA, we should give the corresponding board specific layer, and we have Raspberry Pi and corresponding layer should be given. And then our custom layer, which has the application in it. For example, in our use case, we have a Rust application, which helps in controlling the door. So for that, all the recipe and all the source code and all the ways how it should compile and it should be installed will be placed inside the custom meta layer inside the application. So this is the build environment. Once this is done, we will be setting up the environment and then Bitbake in the target, and then the image will build. So this building an image is not a simple process. It will take a lot of time. So if you are having a high compute instance with more number of CPUs, the build will be faster. If it is less number of CPUs, it will take a lot of time. So for this setting up tool, since we are pipeline into concern, we have something called CAS. It's an Bitbake setup tool, so which helps in with a single file, which helps in creating a full build. So I'll just show you an example how this file looks like. So this is one such example. As I told you, we should specify the layers, and we should specify the corresponding URL that where the layer should fetch from, and finally we should give the target to which it should print. So finally we should build the ECU door target that will be placed and that will be booted into an hardware system. So moving back here, this is regarding the Yocto. And next one is, here comes the software. So once now using Yocto, image has been built. Now we wanted to test it. So for that, first step we are moving is software testing. We'll try to run this built image in a software and try to check it first. So for that we are using QEMU. So QEMU is an free open source VM, or it's an emulator where we can able to run all machine in it. So it will run by use of binary translation. That is, it will convert from one instruction set to another instruction set. For example, NVIDIA, it is having ARM based architecture. Now we are building an application for an Intel architecture. So if you wanted to try this out, and if you want to try an ARM based image should be running, so we should create an QEMU ARM 64 based image, and we can able to run it, boot it up, run it, and we can test on it. So this is the software testing. Currently we have implemented two tests. One is smoke test and one is application test in it. So smoke test gives the basic sanity of the image, whether all the interfaces have been up and whether the corresponding application is running in the background, whether it is connected to the internet, etc. And the application test is the real application that we build should be tested properly. That is, for example, as I said, the door. is an example. So we will be testing whether the door and the information is given correctly and we are getting the information back. So this is the application test. So for the smoke test, we are using gauze. This is very simple and quickly we can able to create our own custom test and we can able to run it. Okay, so moving on to the main pipeline setup. I think ThoughtWorks is disconnected. Okay, again it came again. Cool. Sorry folks, I think there must be some bug. I think now we are back online. So yes, let's moving on. Let's move to the pipeline setup. So this is the pipeline that we have set up for building an image and testing it and storing it in a place. So for that, what we currently have is we are pushing our code to the GitHub, which is the version control. And from we are using Circle CI as the pipeline, a CI/CD setup. And first job is like it will test the application. The first one is the Rust application, and this is and it has dependence on Visum IP, which is a C++ based library. So we are trying to build it in Circle CI and to connect to the Azure. So okay, why Azure VM? So as I said before, Yocto will take a lot of time and it consumes a lot of resources to build a single image. So we are using high performance compute system from Azure VM, which has a lot of CPUs, so that we can able to cut down the time of the build. So that's why we are using VM here. So we are trying to copy all the files which is required for the build to the VM, and then we are building the QEMU image. Then we are testing the QEMU image. And once the image is being tested, it should be saved in the Azure blobs, Azure storage blobs. And then we are trying to build a Jetson TX2 image, and we are storing it right now. The hardware testing is being done; it's work in progress. So if you can see here, this is the work in progress, Raspberry Pi. So when that works. I'm just going to ThoughtWorks. So I think now we are back again. Yeah, so I was explaining this. So after this step, we are working in progress is it should automatically, the Circle CI agent should automatically run on the Raspberry Pi. It should be able to download the built image, should automatically flash it, test it using the smoke test and the application test. And then if all the test case passes, it will again push to an Azure blob and it should be saved like this. So this is the thing that we are working on the hardware side. And we have two workflows. One is like the default the commit workflow. So it should build each other whenever a new commit is done. And another workflow is nightly build. So why this workflow? Because as I said before, Yocto project is a very vast one. So there will be a lot of open source layers will be pushed by different people. So every time different layers will be added and the source code changes. So we need to test it every night so that our application and is running without any problem. So that is why we have a nightly build, which will run every night at 11:30 p.m. So I'll just quickly open the workflow. So if you see here, this is the workflow. So we are testing the application in the first two jobs, and both is configuring the VM and setting up the VM, and then we are building the QEMU image, and then we are testing it. I'll just quickly open the test. So leave up the first few steps. It is just like starting and connecting to the VM, and then we are booting the QEMU image in the background. So we are the QEMU image is built and it has been booted, and then I'm running the smoke test, and then I'm testing the application that as I said before, we are having Rust application in it. So we have Cargo as a package manager. So we are running the test for it, and then I'm once the test case passed, and then I'm shutting down the VM. And then I'm uploading these things to an Azure storage blob. So this is done in the QEMU testing side. And then now TX2 image is being built. Then we are planning to set up the hardware in loop testing also. Once it is done, the corresponding image hardware will be also pushed to the assured block. So this is what we are trying to build as a part of embedded pipeline. Any doubts? Cool. If you have any doubts, you can post it in QA. We'll reply it later. Thank you, folks.
Any questions so far? So what we have shown is basically the pipeline that is being used to build images for the hardware targets that we're going to use. Yeah, and they're going to take up different you have to build layers or different applications that we want to create, and for each of the applications, we can build continuous integration and continuous deployment pipelines. Yeah, what we are still to do is connect the hardware back, runs tests on the hardware so that it can give some feedback to the CI/CD pipeline itself. That's what we'll be attempting to do as we go along, as for the next tranche of things. With with that done, if there are no questions as far as embedded pipelines are concerned, we can move on to the next topic, and that will be Rust in automotive. Yeah. I would like to invite Gnana for taking over the Rust topic as such.
So, thank you, Vivek. Okay. Am I audible? Let me check. Right. Thank you, Vivek. So, now we can get started with the Rust in automotive second part of the talk. So, before that, let's just talk a little bit about Rust. So, why or what is Rust and why it is in the first place? So, Rust is a general purpose multi-paradigm programming language. It was developed in early stages as a passionate project, and then later it was being adapted or being supported by Mozilla. So why they have to support this project in the first place? So it solves a lot of important problems that are there in memory safety, and that are there with performance as well. So Rust offers performance that are in equal with the C and C++. At the same time, they neglect or they avoid a whole bunch of problems that we get in C, C++ in general. So in that place, Rust plays a very crucial role in developing low-level or embedded programming space. It creates more opportunities to build a highly performant or low-level programming with high efficiency as well. So other than that, you can see that it provides zero cost abstraction. So zero cost abstraction generally means that whenever Rust does a lot of compile time checks. So when we do a lot of compile time checks and we generate at the end binary will be more or less similar to the low level code that we will be getting, or the machine, or it will be comparable to the low level machine code. So there will be not much of a runtime overhead that we get in terms of Rust. Moving on. So there are several companies that have been using Rust in production. So, like it's mentioned in the right side. And apart from that, regarding automotive space, important steps have been taken regarding including Rust in the ecosystem. So, AutoSAR is one of the important, say, a very crucial member in automotive space. So, AutoSAR is we saw in this previous talk. It is a consortia that has been formed to create standards for automotive development. So different companies come together and say they set certain standards for automotive development or software development space. And they recently announced that they are creating a working group for the Rust programming language in the autonomous automotive space. So this is a very important update because this will be very crucial in bringing Rust into the ecosystem. So what we are going to do using Rust in our use case. So it's a very simple, or say it's a straightforward application. So we have two different ECUs and it will be running an Rust application in it. And we have we have a communication stack. So that stack can be any communication protocol, say TCP/IP, UDP, and we have an OS. And then we will be interacting with this ECUs from the command line. So that is the idea that we have to showcase as to bring Rust into this ecosystem. So in that direction, the first thing that we currently tried is that we are using some IP as the communication protocol. So and since some IP is in C++, so some IP currently we don't have any repo or open source repo that is available for some IP in Rust. So some IP is currently available in C++. We used that some IP in C++ implementation, and we wrote as or say we wrote what are the things that we needed in Rust, in our Rust application, and we wrote a CXX wrapper. So CXX is another Rust library that we use to achieve this particular interoperability. So in this stack, if you see that it is similar to the previous one, we have an ECU in the left, we have a server running on the Rust server running on the ECU, and then that Rust server will be talking to the some IP, which is wrapped, which has a CXX wrapper, provides the Rust bindings. It is running on a Linux system, and both and like you see that there are little Rust symbols on nearby. So currently this Rust server application is in Rust, and Rust client application is in Rust, and both the some IP and the client and server both are in having CXX Rust wrapper. So this CXX is nothing but like I said, it's a Rust library which helps us to interact with both the Rust and C++. So you can use the Rust code in C++ and C++ code in Rust. So that is the main idea behind this library. So we can also use some shared structures between those languages as well. So if we define a structure in C++, we can use the same in Rust. So we will be moving on to the code, and let's see some implementation regarding this. Okay. So this is the server Rust server application that we have. First, let's take a look at the file structures. We have the CPP, which is the C code or the vsum IP code. So vsum IP is the library Git repo that we use. It is basically some IP implementation of in C++. So we have that. We use the vsum IP, which is developed by Covisa, and we also have the source folder, which is basically our Rust application. And then we also define the dependencies. So if you take a look at the dependencies, we have the CXX in the dependencies. Let's start from the C++ side. So we have defined a server. So this is basically a C++ class. We have included the vsum IP. So vsum IP in this case is like a shared library. We have included this vsum IP while in our Ubuntu as a shared library. And then we are defining the methods. So we have two methods like message callback and then start. I mean, we have several methods, but we will be using only the start method in our Rust application. And also the message callback will be internally calling the Rust part. So we'll be going, let's move on to that. Let's go into the Rust implementation. So in the Rust part, we have the CXX bridge. So this is where we will be defining that a CXX should be knowing that we are using this module to interact with the C++ and Rust. So here we have several three different blocks. Say the first block will be like common for both Rust and C++. The second part, Rust, extern Rust, which we expose from the Rust to the C++ side. And the third one is the C++ block. So whatever the code that we use in C++ can, it is defined in C++. We are making use of that in our Rust. So here we defined, in our C++ code, we defined start. And we also have another standalone function, new server. Cool. So this is the CXX part, and we also another thing to add here is that we have the message callback. So this we have defined this message callback to use message. So this message structure we have defined in common, like it will be known both to C++ and Rust. So here we are defining the message to have a data and length field. So in the C++ part, if we go to the implementation, we are using whenever we get a message from the client, so whenever that message will be of the type vsum IP message, so we are creating our own message structure here, and then we are passing that message structure to the Rust. So this message callback is essentially a Rust function. So this gets called, so that whatever the message we receive from the client is being sent to the Rust. And in the Rust side, if we see, we are making use of this method to process, and we will be sending the response as a string. And this string will be in turn sent by the C++ server to the client. So this is the this is the system that we currently have. So in order to do something, or say to make something work in quick time, so we implemented a wrapper on top of the existing C++ some IP implementation. So let's take a look at it in action. So we have the client running in this terminal. If you see, it is client, and then it is running on the ID 5555. So this is the ID of the client, and we have a server running on another port. So this is sorry. So this is running on the port 4444. So let's try. But so what the use case that we have taken in hand is that, so we have an LED door. So consider this. Let's go back to the diagram. So consider this this ECU is handling the door status. So whenever we need to open a door or close the door, so this ECU is handling that. So and this client will be sending some messages to open and close the door. And in order to get the status from the server, we can run get door. So we are receiving status open. So these commands I have run previously. So we are getting now the currently the door status is open. If we need to close the door, we can send the command. So this whatever the message that we have is being defined by us. It's I mean there's no interlink protocol, but we define the messages to interact. So now the door status is closed. If we get door again, it is being closed. So this is the this is the POC that we did to explore the some IP with CXX wrapper. And moving forward, we would like to try, or we want to do, is that we need to implement the some IP in itself in Rust. We don't want to depend on any CXX wrapper. We need to use this some IP in Rust so that we can achieve much more performance. We can do benchmarking, and if I'm sure that using Rust will be much more efficient and performance while comparing to using C++, and we will be losing lots of bugs as well. I mean memory bugs as well. So that is our next direction. So we need to move into some IP implementation in Rust. So what is this some IP? The some IP is a scalable service-oriented middleware over IP. So if we split it, what a scalable service is nothing but some IP is basically defined over service. So it is like whenever we need to get any messages. Say for example, it has two different modules. It has request and response module, and it also has this publish and subscribe module. So whenever the client need a request, client sends a request, then only it will be getting back a response. So basically it is a service, and then we have the middleware. So some IP is built on top of the TCP and UDP. So it can use both TCP as well as UDP as well. So it will be using TCP when it is working with request response, and it will be using UDP when it is working with the sub model. And so these are some of the features that some IP provides, like serialization and remote procedure call. So remote procedure call is when we will be using we'll be sending a code, say invoke a procedure in server from the client side, so that we can do that in some IP, and then we can also do service discovery. So service discovery is the base of this some IP. Why? Because the ECUs will be saying that expose a service, and then the client has to find the service, and then it has to send any responser or say subscribe to a service. So it should be configurable from the client side. So basically the server will be offering a service, and then the client will be finding a service to subscribe to it. That's where publish and pub/sub model is also there in some IP. And the messages also, we can send a huge number of, I mean, say the payload can be really huge, because we are using very high computable ECUs. So in that case, we need a protocol that can handle a large amount of data. So some IP is also providing us that feature as well. So that is basically some brief intro about some IP. So so to kind of conclude, I want to say that we are currently working in this direction. We are currently trying to write some IP in Rust. So we are happy to collaborate with people and get some ideas from the larger community. And then we are looking in the direction to make this library as an open source project as well. So that is what we have as a larger context in mind. And yeah, I think so. If there is any questions or queries, we can take.
So if there are any questions, please post on the chat, or we can also take those questions if you can ask them. Okay. In case there are no questions, that would be Geek Night this edition at Coimbatore. Thank you everybody. Thank you everybody for joining us both at remote and here. Thank you so much.